Good evening, everyone. Welcome to today's problem solving section, week 5, digital VLSI testing course. So, today we will see about the testing of two other faults. Like in the previous week, we have seen the stucket fault model and how can we generate the test pattern for the stucket fault model. And we have used the three algorithms, ATPG algorithms like D algorithm, Odom algorithm and fan algorithm. So in this week we will see the delay fault as well as the bridging fault and another type of testing known as built-in self-test. First we will start with the delay testing and the so the delay defects, the output will be correct, but the correct output will be obtained after a certain delay. So when we have a circuit which is running at a slower speed, the delay defect is introducing some amount of delay, and like for example, if we consider that at this point of time, say t is equal to 4 unit, we wanted the correct output which is say a is equal to 1 and say at t is equal to 6 units, t is equal to 6 unit, the output to be 0. So it's like 110. But because of some delay defect, the output is 1 for this unit and it remains at 1 and goes to 0 at this. So this delay, the functionality remains the correct, but delayed output is obtained. So you can see that there is some delay, because of which if you want to capture at this point, if capture at this time frame t is equal to 6 unit, the output is actually erroneous. So that means if we are running at a slower speed and say we are capturing at this point, the output could have been correct. That means the delay faults affect when the circuit is working at the high speed, and the circuit affect when the circuit is operating at high speed. Some of the delay defects get detected by testing the circuit at speed. So we call that as at speed testing, where the testing is performed at a high speed or the operational speed. So for this delay faults, The stuck fault model is insufficient to model all the delay related defects. So we want a separate model for the delay faults. So the delay fault model is path delay fault, transition delay fault, and segment delay. So first we will see the path delay fault model. It will model the combinational path, like the so this models for the combinational path in a circuit and considers the cumulative effect of the delay along the path. So in the path delay fault, we traverse like consider the path, and in the path the total delay, cumulative effect of delay along the path. So here we have, if we consider a path, then we will have two types of inputs, which is on inputs of a path and off inputs of a path. A transition is launched at the start of the path, and the test must propagate the transition to the end of the path. So if you have some circuit, so like this, and we say that this is one path, so a transition must be launched here and must be propagated to the output. So this requires two test vectors, and we call them as V1 as the vector which is required to initialize. So we call this as initialization vector, and V2 vector which is at like we have applied it, and next we launch the transition as well as we capture the effect like output of the combination circuit. So it's a launch and capture vector. And also you can see like this path, if we consider in any circuit, it will be increasing exponentially, like number of paths can be exponential to the number of gates in the circuit. So for any given circuit, for with n gates, the number of paths can be like if number of gates increases, then the number of paths can increase exponentially. So next, the classification of path delay faults. We have statistically sensitizable, which means all of inputs of a path P can be assigned to non-controlling values by some vector. And the second is the single path sensitizable, where all off inputs of a path can be set to non-controlling value for both the vectors of a test. And false path, a transition can't propagate from the start to the end of the path. So not all necessary off input values to be set to non-controlling values simultaneously. So this I think we will discuss briefly. Statistically sensitizable single path sensitizable So what we say is has the statistical sensitizable path is that all of the off inputs of a path can be assigned to a non-controlling value by some vector. If we see that this is a transition, that means if I consider this path, then this value I should be able to assign to some non-controlling value at least for some vector. For some vector. But here, because it is a fan out branch, both have the same transition, so we cannot sensitize this path. We had a transition here and output also we have the same transition. So this is unsensitizable path. So we have next is the robustly testable paths. So the single path sensitizable is too strict. In the single path sensitization, the condition was that the off path input should be non-controlling for both the vectors. So here we will relax it based on the transition made, whether it is a controlling to non-controlling transition or a non-controlling to controlling transition. So here may not need to set all the off inputs to a non-controlling value in V1 in order to propagate the transition. So if we have this as the path which is highlighted, we have a transition which is high to low. This is a controlling value. So, and this is a non-controlling value. So we need a 0 and initial value can be anything because this is going to control. So this can be anything, but this is 0. So here we want a 0. So here we have relaxed the first vector to be don't care from the single path sensitization. And next now we have got the transition here. To propagate this, the AND gate output 1 should be 1 and the next also should be non-controlling, then only we can propagate this. So this is called steady 1 or strictly 1. So that transition is obtained here. Now for this, if you see it's 1 and 0. This 1 is a controlling value. So anything here will not be affecting this transition. Now for 0, we need a 0 so that this 0 can be propagated here. So again here this are called as the off path inputs and this are called the on path inputs. The inputs which are in the path where we are propagating the transition is called as the on path inputs and the other path like this or this are called the off path inputs, and this is also an off path, but this off path requires both the vectors to be 1. So this is the robustly testable paths. So here we have just given that okay, this value is going to control, so we can have a don't care. We will just write them as a statements. If a path is robustly testable, then the corresponding test can verify the correctness of the path, irrespective of the other delays in the circuit. So we have in the path delay testing two types, like here we can have a robustly testable and non-robustly testable. In the robustly testable, there can be other delays also. The next we will see where we are going to test non-robustly, where we consider that that is the only delay fault we are having in the circuit, that no other delay faults are present. So if a path is like robustly testable, that means other delay faults can also be present in the circuit. So now how to choose the value for the robustly testable path? When the corresponding on path of a P has a controlling value, has a transition from controlling to non-controlling, the value in the first vector for the off path can be x. See, when we have a controlling value to a gate, see, these are the two gates. This is a gate. If I have a controlling value here if it is 0 or 1, the output will be this controlling value only. So the starting first vector is controlling vector. So we can have an x. The second vector is it is transitioning to a non-controlling value. And here we need the off-path input to also be a non-controlling value in order to propagate this non-controlling value to the output. Therefore, when we have a transition from controlling to non-controlling, this first vector can be don't care and the next vector should be a non-controlling. This was the we got this improvement from the single path sensitization, where in the single path we needed both the vectors to be non-controlling value. Like it should be either strictly 1 or strictly 0. Here we got that relaxation in the robustly testable, where the first vector can be don't care if we make a transition from controlling to non-controlling. Next, if we have a transition from non-controlling to a controlling transition, that means V1 is a non-controlling value. To propagate this non-controlling value, the other input should also be non-controlling. And the next vector is a non-controlling. To have the transition, we want the next vector also to be non-controlling. So this off path must be steadily or strictly non-controlling value for both the vectors. So these are the criteria for the values we want to assign for the off path for the robustly testable fault. Now non-robustly testable fault, so there are no other delay fault. Not all paths are robustly testable. So further we relax the requirement for V1, the first vector. But this test is valid if the circuit has no other delay fault. So if you want to propagate this transition to this path, in the robustly testable, we have a transition here. For an AND gate, this is a non-controlling. This is a controlling. Then if we had a robustly testable, this should be strictly 1. But here, that means we cannot test this path robustly. But in non-robustly testable, we assume that this is the only path which is having a delay fault. So here we have another transition, which is say 1, 0. And because of the delay, like this output could have delayed this much, and this remains the same. So we have this one because of the delay. And if we want to observe at this node, the output is 1. Here it is 0. Ideally, it should have been 1 and 1, 0, 1 and 1, 0. So this condition we have relaxed. So this highlighted path is non-robustly testable. Next, ATPG for path delay faults. We use a new value algebra to consider both vectors simultaneously during the ATPG. So now we need a different set of values where we said that strict 1 means both the vectors are 1. Strict 0, both the vectors are 0. And a relaxed 0, which is a don't care 0, don't care 1. And when both the vectors are don't cares. So this logic, we will use it, and the truth table for the basic gates are, this is like strictly 0, don't care 0, don't care 0, 1 1, don't care 1, both don't care. So whenever for an AND gate 0 is a controlling value, so we get a 0 here. And this means we have the second input to be 0, but this is both 0 0, so we have S0. For S1, this is a non-controlling value, so this should come here. Similarly, for U1, this S1 will be a don't care here because of a don't care here. So, similar way for OR gate and NOT. Any doubts?
Hello, ma'am.
Yes.
How can we differentiate between single path sensitizable and statistically sensitizable?
No, the like this one,
Yeah,
we are not able to sensitize using the single path, single like testable, because we are not able to launch a transition and propagate the transition. Both the places we have the same transition, so any effect could have been masked.
okay. Yes, ma'am. Thank you.
Okay. Why are we using this algebra? Because we wanted two vectors, v1, v2, where v1 is the initialization vector and v2 is the vector for launch and capture. And we have seen that for testing, two vectors are needed, and for both the vectors, we want to define whether it is a don't care and the logic 0 or logic 1, or whether it is like strictly 0 0. It is 0 0, it is strict 0. This portion we don't know, and this is 1. So this we call u1. Again, this first vector we don't know, and this is 0, we call as u0. If we don't know both the vectors, this don't care condition. So this is our new, and now to propagate the fault, we need to know how this values will be with respect to an AND gate, OR gate, or a NOT gate for a basic gates. Is your doubt clear? So these are some methods for generating the patterns, where an algorithmic method to generate the delay test pattern, where we start from the primary input and perform a depth first search so that we can get what are the paths, and then we generate the test pattern. So this is some this is an algorithmic approach, recursion based path delay fault ATPG. So I'm just skipping this, and next we have transition fault model. So we have seen that there are exponential number of paths. So next we come to a TDF, transition delay fault. Assume a large and a gross. This assumes that there is a large delay present at a circuit node. Previously, it was considering the cumulative effect, like if this was the path, the complete cumulative effect from the path. This gate could have added the delay, this gate could have added the delay. So this gates could have added and the cumulative delay was considered. Now we consider that particular node, circuit node, is having a larger delay. So irrespective of the path, the effect is propagated. The gross delayed effect will be late arriving at a observable point. So this is most commonly used, and it is the number of faults are now linear because every circuit node only we are going to consider to have a larger delay. So number of gates with respect to number of circuit nodes is going to be linear. And also two vectors are needed to test as before. So now here we will have slow to rise or slow to fall delays. So a node X slow to rise can be modeled simply as two stacked faults. This is a slow to rise fault model where it is taking time to rise from 0 to 1. So this can be considered as here one stacked fault, here one stacked fault. So first time frame X by 1 needs to be excited. Like if we consider here it is a stacked one, we need to excite this by applying 0. Next second time frame, if we consider this is stuck at 0, we need to excite by applying 1. And then we need to propagate this output. So x0 needs to be excited and also propagated. This is like similar considering to stuck at faults. And transition fault testing. Say we have one node x which is having slow to rise transition. Say this. We apply a 0 here through this primary inputs. We got this 0. Next we apply a 1. We have initialized this node to 0. Now we have applied this 1 and we need to propagate this to some primary input, and we have got this transition. So a transition fault may be launched robustly, non-robustly, or neither. So a slow to rise at output of an OR gate. If we have this as slow to rise OR gate, then we both, if it is slow to rise, then we will have a transition slow to rise here. To have a slow to rise, if we consider this path, this is a slow to rise. To have a slow to rise here, a non-controlling value is required. And this is a NOT gate, so an opposite is required. If we have this value, And here it's already a non-controlling for the NOR also. So we have the same transition. So having both the transition, we can have the transition at the output. So we want this slow to rise transition. And this node, if it is having more delay, so this transition will automatically be delayed. So it doesn't depend on the path. It's not like the other path, the other node is having some delay, which is like any other node value like this, and this cancelling effect is not seen here because this node is going to have a delay, so the output will be obtained after the delay. With this, we will go to the next fault model, bridging fault. So this models shorts between two circuit nodes. Previously also we have seen say this AND gate. If this node is there is a line for VDD if we consider, and if this was short to VDD, this node is going to permanently remain at logic 1. That means this is stuck at 1. Similarly, if this node, if we have a ground line, and this bridging fault can be because of a defect which is a material, say this is one metal line, this is one metal line connected to VDD, connected to this gate output. Some material is coming in during the fabrication process connecting between VDD and stuck at 1. So this node is always stuck at 1. Similarly here, this node is always stuck at 0. Can you please explain what is the cumulative and node delay concepts? Say I just take one small circuit. Uh, Now if I consider this path and say that this gate is adding some 1 unit of delay, this gate is adding 1 unit delay, 1 unit delay, the total output will be obtained 3 units of delay. So similarly this path, so whenever an output has to come through this path, because of this gates, they are adding some delay, so it's a cumulative effect. Now node delay means this output, like if I consider this node delay, okay, I need to if from here I connect here. So if the output could have propagated from this path, it could have seen 2 gate, and if it is propagated from this path, it could have seen 3 gate. So this is for the critical path concept. So I'm just coming to our node delay. Now if this node is having say slow to rise transition, say of 2 nanosecond, now when we propagate this output is affected because of this 2 nanosecond delay, because of this gate, this node delay. Here it's given that output of an OR gate, this has slow to rise delay. So this transition are same. So output will depend on this node delay, and the OR output should have been this, but because of the delay it is delayed, and at this capture phase we got a faulty output, like the fault is observed. Similarly, like if we say this same circuit for cumulative, then either this path could have added a cumulative delay or this path could have added a cumulative delay. But this is like single node is adding a delay. Uh, is it clear? Is your doubt clear? Yes, the concept is, so the only difference between path and transition delay is this concept. Yes, the path delay is for the cumulative delay where each node is adding some delay. So, okay. For the path delay, if we have a critical path, then there will be like, if we have a critical path, this is a critical path. So, it will be the longest path which has high chances of affecting because of the added cumulative added delays. The transition delay path is like we want to excite a transition and we assume that particular node is having a delay, so that transition will be delayed at the output. Did I clear your doubt? Okay. So the bridging faults models the short between the two circuit nodes. So this one, the stuck at 0, stuck at 1, we have already like seen before. So now the bridging fault is not excited unless the like, now if this is a wire, this is a wire. say x. These two values are shorted because of a bridging fault, and this fault will be excited if both the values are 0 0, then the output will be 0 0. So we cannot excite the fault. If it is having opposite value, then this fault will be excited. That is, the bridging fault is not excited unless the two circuit nodes have opposing logic values. So the faulty value depends on the bridge fault type. So there are few types of bridging faults which are AND bridge, OR bridge, X dominating Y type of bridge, X dominating one Y bridge. That is, X dominates Y. This one for a specific logic value, that is if X is equal to 1 and X dominating 0Y, that is X dominates Y if X is equal to 0. So this is modeled has shown in here. The AND bridging, there is an AND gate between these two wires. So that's called AND bridging, and this is for OR bridging. X dominates over Y means whatever the value of Y, the output is X. And whenever this is 1, the X will dominate the Y. Whenever this is 0, the X is dominating over the Y. That is why dominate 0, dominate 1. So this is how these bridging faults are modeled. Now if we consider that this bridge, we said that if we have opposite values, we can excite this type of fault. Now what will be the output? Both are AND gate output, which is 0 0. But the true value should have been 1, because it was the line like this. If it is 1 0, it should be 1 0. So in this way we can deduct this bridging faults. Any doubts here? Next is the bridging fault ATPG. This is This is modeled as a constrained stuck at ATPG. So if we consider an AND bridge, we can like deduct x is stuck at 0 with setting y equal to 0. If this is x, this is y, this is stuck at 0. If we apply 1 here to excite this and a 0 here. This example we have already seen. And similarly for y0 with setting x is equal to 0. This is the, here we have set 1 0. If we have 0 1, again this will be 0. This will be, should have been 1, but because of fault it is 0. So conventional stuck at ATPG can be modeled to handle this bridging fault, like to generate the patterns for bridging fault. So next is the test compaction. So we want to reduce the test set size to reduce the test storage and the test application time, because ATE, the structural testing we use ATE, which is automatic test equipment. We have a some memory, and ATE is costly, so we have to factor time and memory. If we can reduce the test set size, memory will come down and also the test application time will come down. This is the test application time. So we want to reduce the test set size. That is our objective. So if we have, say, a fault list, a set of fault will be detected by each vector. This can be identified by performing fault simulation. And as we go down with the patterns, the number of faults getting detected will reduce. So there are few methods, like we generated the pattern in this way. Can we simulate in this way and check? Can we drop some more test some of the test patterns, like which could have been detected by some other vectors here, like so. Also, okay, we will see the methods. So the idea is to find the minimal set of vectors that can detect every fault. So first we need a detection dictionary like this. So the test set compaction, vectors are incompatible. Wait a second, I need one more slide. Test set compaction. So the vectors are incomplete. Like if we have an circuit, we have like seen that most of the time, say this should be 0. If we have a fault here, say stuck at 1, so 0 is needed to excite, 1 is needed here. So we get fault free is 0, faulty is 1. The output should be 0 bar 1, a 0 is needed here. So either it can be 0x or x0. So you can see for this simple circuit, that we have some vectors which are unspecified, or this pattern like 0 1 x 0 or 0 1 0 x. These are the incompletely specified patterns. Patterns, or you can say vectors. So some of the vectors can be compatible. What is compatible means, if we have a vector like this and a vector like this, they both are compatible. That means they can be merged to give one pattern. One, this is don't care, one, this is 0, this is again I don't care, but we need a 0. So this vector 1 and 2 can be merged to give this. So this two patterns we have merged to one test pattern, and now this is sufficient to detect the faults which was detected by 1 and also which was detected by 2. This is one method based on the compatibility. Second method is the reverse order simulation. We have generated the test pattern in this order. Can we simulate and see what are the faults detected by this? So if all the with these patterns, if we can detect all the faults, then these patterns can be dropped. And we simulate from here. So it's a reverse. So reverse order simulation means simulate the test vector in reverse order. Some vector may no longer be needed. And how we draw this compatibility graph, I will take one example. If we have T1 is compatible with this and this vector, and T3, that means T1, T4, T4, T2, T1. So this can be merged to one test vector called T mu. Now instead of 4 vectors, our new set will be only this. So from 4 we can reduce it to 2 based on this compatibility graph. So what is this is, if we have particular bit in T1 is equivalent to T2, or either that bit is don't care in first vector or in the second vector. That's how we have seen the compatibility. That means if these three conditions are satisfied, then T1 is compatible with T2. And in the reverse order simulation, we said like, okay, if we have T1 deducting 1, 5, 1, 5 and 9 fault, T2 deducting 2, 3, 15 and 16, T3 is deducting 100 and 101, 50, 50 is deducting 60, 70, 1, 2, 3, 5, 9, 100, 101. We could have, in the reverse order, we could have simulated this first. So we could have identified and dropped all this fault. So no need of this pattern. So these are the two methods by which we can reduce uh, the methods to reduce the test pattern size includes reverse fault simulation as well as the test compaction, where we have a compatibility graph and we merge it based on the compatibility. The test set compaction. So here this is the fault F2, which is detected only by the pattern V4. So we can say that V4 is essential. F1 is denoted by two vectors, F3 is also by two vectors, F5 by three, but F2 is getting detected by only V4. So V4 is called as the essential. V4 is essential. So these are called as essential vectors, a vector that detects some faults that no other vectors can detect. So a set covering algorithm is applied to find a minimum test set such that every fault is covered. So we said V4 is required. Now if we consider V3, this will be detected, this will be detected, and this will be detected. Now if we have V1, this will be detected and this will be detected. So this is not required. We can drop V2. There may be other possible combinations. Also, this is one possible minimum test set. So this I have already covered. Now N detect ATPG means a fault if we have once we got a vector v1 detecting this fault, we dropped this fault. Now if we have n detect, we will wait till we have n vectors detecting this fault f1, then only we will drop this. If we have 2 detect, once the fault is detected by 2 vectors, we will drop that fault. So let's read. Idea: detect every fault at least n times. So n vectors that can detect must be different. Although the same fault coverage, if we have n detect, the fault coverage may not increase, but the defect coverage will increase. What is defect coverage means? If we have uh, say x stuck at 0 is detected by y equal to 1 and the other is y equal to 0. So some node, this node stuck at 0 is detected by y, some gate g, y is equal to 0 or y is equal to 1, that means both. Then the bridging fault between x and y could have also been detected. Like defect coverage increases with along with the stuck fault, some bridging faults also are getting detected. So ATPG can be modified for n detect. Now ATPG before V1 detected F1, we dropped the F1. Now we have to keep the F1 in the fault list till we have n times the detection of the fault. So n detect increases the defect coverage, not the fault coverage. Can't say increases, enhances the defect coverage. So the concluding remarks, we have seen these ATPG and the delay and bridging defects. What is n defects? So with this we will go for logic BIST. BIST means built-in self-test. So once if we consider a circuit is under operational and it's not possible to take this chip and come and keep it inside in an ATE machine and test it. So we want to verify the correctness of the circuit when it is in the field operation. So we need something called as self-test. So traditional test techniques become quite expensive. These are some of the problems in today's semiconductor testing. No longer provide sufficiently high fault coverage. Why do we need built-in self-test? Okay, this is We need it for mission critical applications. Some faults which cannot be like we are modeling a defect and detecting it. Some faults which are unmodeled faults can also be detected by built-in self-test and provide remote di- diagnosis, also testing. Okay, so the BIST can be done in two ways. Is there any slide? No. Online or offline. Online means the system is on. That means system is ideal for some time. Say the system is on but not doing any particular work. That time it can be tested. So it's called non-concurrent test. System is on and in the normal operation. Along with that, if we are testing, we call as concurrent test. And offline mode, we change it to the test mode and then test it. So we can either have structural test or functional test. So in the normal structural testing, we have an ATE which has some memory which stores the. Okay, I will just draw this in the next page. Okay, for an ATE based testing, the structural based testing, which we perform after the manufacturing, we have an automatic test equipment which stores the test patterns in a memory. It has the ATE channels which connects the circuit under test. In this way, we apply the patterns and AT will get the see the output and verify whether it is correct or not. In the case of a logical BIST, there will be some test pattern generators which you will see either it's a linear feedback shift register or a method like counter which will generate the test patterns and apply to the circuit under test. We will have an output which will be analyzed by a response analyzer and will have this will have the golden values. We'll say whether the circuit is having a fault or not, and this will be applied to the BIST controller. This controller will say, okay, generate the pattern, apply it, and this will apply the pattern. Output will be verified by the response analyzer, and we will be like given the output whether it is a faulty or fault free. So this is for offline BIST. Here it's coming to the test mode. So the logic BIST requires much more stringent design requirement restriction when compared to conventional scan. So therefore, when designing a logical BIST system, it is essential that circuit under test meets scan rules as well as BIST specific rules. So this scan rules we have seen already in the initial classes. Now we will see what is the rule specific for the BIST. So if we have a don't care value and that is propagating to the output, then we will not be able to get to know whether it is output because of the fault or because of the don't care. So the system may predict it is faulty, but the output may be different value because of this don't care also. So we need to block the don't cares. So either we will use a zero control point, that means this will be 1, BIST mode is on, this will be 0, so output will be 0, so that node will be always set to 0. And for an 1 control point, this value will be 1 in the BIST mode, so the output will be set to 1. Or we can either bypass this when we have a BIST mode 1, so this value will be at the output. Next is that control only scan point. If we have a scan flip-flop, this D value we can apply. So if this is either 0 or like whatever is applied from the user, means the test pattern will be obtained here. And in the normal operation, 0, this X will be propagated from the 0. And similarly, we can have the scan point where like we can even have a scan enable and shift in the patterns. X bounding methods, depending on the nature of the unknown, several X bounding methods can be used like
तीनों प्राइस के आगे ना एक क्रॉस लगा दो. हाँ हाँ लगाओ लगाओ, लिख रही हो तो फिर आज पूरा कंप्लीट करो.
so common problems are increase the area of the design and impact the timing. Why it is increasing area and time and the timings? Because we are adding an AND gate or OR gate, and that too if it is in the critical path, then it's going to impact the timing also. Or in other paths also, if it is going to add more delay, then that path has high chances of becoming a critical path. So it's going to change the timing, also the area, increase the area. Why we get an unknown? Because there may be some analog blocks. We need analog blocks for interface with the real world. Or maybe because of the memories. Memories are like based on whatever we write or read, so that values are unknown. Or there may be any combinational feedback. So such sources from where we obtain unknown values, we bypass by adding the logic like control points or some scan point. If we have an asynchronous and set and reset signal, so one of the source for unknown, so we want to block this when we have the BIST operation, but that is the test mode. But if you want to test this asynchronous path, we can test through this SRCK path. So using the existing scan enable signal to protect each shift operation, and by adding a set reset clock point on each set and reset signal, or reset signal to test this circuitry. If this is one in the scan enable mode, so this is 0. So this is blocked. But when this is 0 normal operation, based on this, we can test this path. So for example, here it is 0. It is in the scan enabled mode. We are shifting in the capture phase. We have captured the required value. So we will shift out the pulse. Now, if you want to test the set or reset circuitry, we will enable this. In this phase, SE should be 0. So this for set or reset value could be have been captured. So we have to shift out that pattern to the output. So we apply a 1 here and we shift out that pattern. Typical unknown sources, a tri-state bus. Okay, so if this node during our normal operation, either this or this could have been in the on state. But in the testing process, we don't want both the buses to be on, so we want to mask. So we use one hot decoder, which means any one time, any one of the this tri-state bus will only be on. Say if both are on, X nor will be 1. This will be BIST mode. So BIST mode, if it is 1, this is also 1. That means this will be 1. This will be 0. This will be 1. This one will be applied here. So this is enabled, whereas this is 0. So this is disabled. So we can see that at a time like one tri-state buffer is on, not the both. If we have one enable both, we have enabled one. This is also enabled. This is also enabled. Both will be on. There may be false path which can also be a source of unknown. So we can add a 0 or a 1 control point. And other are the critical paths. Like in the critical paths, if we are adding an extra input pin to a selected combinational gate on the critical path. So this control methods we have seen. So if we have this unknowns, either we can have 0 control, 1 control, or we can hold that scan cell to a particular output state. And also any other node inside internal modules are not allowed to float. Only the primary input and primary output are allowed to float, like, and that must be properly connected to VCC and ground. And internal nodes should not float. If a node is floating in a circuit, then this will have a high capacitance. So any noise in the surroundings can change this value. So it's like don't care only. Bidirectional IO ports. So this is a bidirectional IO port. So now to fix, we want to fix the direction of the bidirectional port. So we are in the BIST mode. Say scan label is 1 or whatever is the scan label. This will be 1. This is 1 means we enable this so that we have fixed this direction to be this direction. So similar circuitry can be added here to fix it from output to input also. Sometimes we need a retiming because there may be some hazards or races caused by the clock skew and may occur between the test pattern generation and the scan chain inputs of the circuit under test, as well as between the scan chain outputs of the circuit under test and the output response analyzer. To avoid these potential problems and ease physical implementation, we recommend retiming. So how we perform retiming is by adding the flip-flops, two flip-flops, and for output analyzer again two flip-flops. So here same, and here the inverted flop, and here also inverted flop. Now we are like studying about the built-in self-test. So how to generate the test pattern for the built-in self-test. So we have already said that it can be a counter or an LFSR. So we can generate the test patterns using LFSR, which is linear feedback shift register. So the test patterns can be exhaustive testing, pseudo random testing, pseudo exhaustive testing. So this can also be generated using either counters or cellular automata. So in LFSR we have two LFSRs. LFSRs includes two LFSR, standard LFSR and modular LFSR, where in the standard LFSR we have the XOR gate outside. I'm just showing the modular LFSR. Here it's in the path. Functionality wise, both modular and standard have the same functionality. Structurally, they are different. That consist of n d flip-flops and a selected number of exclusive OR gates. So this based on this h value, if this h is not present, this XOR is not needed. And similarly here we will have in this path between the D flip-flop. So each XOR gate is placed between the adjacent D flip-flop, and this is easy for extension. We want one more, we will just add one more and then connect it. So extension is easy here. So the internal structure of the end-state LFSR can be described by the characteristic polynomial, which is given by h1x. So this h1 can be 0 or 1 if we have a feedback or not. So S is the value that is the content of the flip-flop. Now we will come to this problem. If this is the LFSR, standard LFSR, then we will start with this pattern. Any one of the bit should be 1, like we will not start with all zeros as a pattern. So if we see, this output is XORed with this and this. So it should be 0. This and this, it should be 1. So in this way we will obtain, and it has how many patterns? Total 6 patterns. After that it starts to repeat. In the modular LFSR, we have this XORed with this value to store in this register. And always we will say if this is X4, 4 flip-flops, X4, this is always fixed. We cannot control the X4. Now what is S0? It's because of the feedback, this will be coming here. Next is what is the primitive polynomial. So we said that there are 6 patterns that can be generated. Now in the primitive polynomial, sorry. So these are being found by the analysis that some of the primitive polynomials, if we have n is equal to 25, if we have this primitive polynomial, then we can generate set of all the values. So this will be generating all the patterns, I think, except 0, 0, 0. If we have, say, f of x is a function, so the polynomial is something like 1 plus 2 x power m, where m is 2 to the power n, where n is the degree. So if m is equal to 2 to the power m, that means it will be like repeating all 2 to the power n minus 1 patterns. Because if we give all 0, then it will be stuck at 0. So except all zeros, like all zeros. So any polynomial which can generate 2 to the power which repeats after 2 to the power n minus 1 vectors, those polynomials are known as primitive polynomials. This has been experimentally found the values for a primitive polynomial. What is exhaust testing is that we want to apply 2 to the power n all the combinations to an n input for the circuit under test. So exhaustive patterns we can use either the binary counter or LFSR. In a complete LFSR we can also generate all 0 patterns. How to generate this? Let's see. Binary counter, this is the normal like binary counter to generate all the patterns. Next is the complete LFSR. Now we have this NOR gate. If it is stuck at all zeros, this NOR gate can change the state. And this is the minimized version, and similarly for the module. So if we say all are 0, and this value is 0, this is 0, this is 0, that means all 0 gives 1. And this was a 0, so it feedbacks 1. So in this way, the circuit can come out of all 0 state. So that's why complete LFSR can generate all the patterns. So weighted LFSR, so it will have particular, like if this node has to be 1, this is an NAND gate, and this node has to be 0, then both should be 1. So we have added a weight differently for having this node to be 1 and 0. For 1, either 0 or 1, or 1, 0 is enough. So this way we have the weight. So this is called weighted LFSR. And I think it's 725. So I'm just here. If we say that the method is effective in the combined LFSR when the W is much less than N, and this technique requires more tests than other schemes when W is greater than N by 2. This is needed for solving one question. Here we have some linear phase shifter. Before we had some other LFSR. So this is combined LFSR. Another method that in the circuit, if we can count the number of ones, and then if there are 100 ones and the fault has made 101 ones, then the fault is detected. But there may be error in this type of detection due to aliasing effect. Say we have a fault like F1, we had 100 ones initially, and the fault F1 made this to 99 one, and fault F2 has made it to 100 ones. So we will say that no fault because we got 100 ones. But this is not true. So this is called the aliasing. And we have formula for aliasing probability also. So this is the we will go with this. We'll start the questions. Why do we need two vectors to detect path delay faults? So this we have said that first vector V1 is for initialization and second vector is for launch and capture. Launch and capture. So option C. Yes. Second question. According to the value criteria for a robust testable path, if the on input of P undergoes a transition from controlling to non-controlling, then the off path input should be. We have said that this is controlling value. So whatever is this value will not affect, but here we need non-controlling. So this was the vector. So the first can be x while the second should be non-controlling. First vector is a controlling value from our on path. So it's already controlling value. Any gate input, if it is having controlling value, this output will be this controlling value only. So this can be any value. Going to the next question. Find out the output of the following circuit using the 5-valued logic shown in the ATPG for both the for the path delay. So this is strictly 0, so it should be 0, 0. This is x0. Now let's come to this NOT gate. Should be both 1. This NOT gate, don't care 1. This is an AND gate. So any input 1, we don't know output. Any input, both are 1, 1, output is 0. Again for NOR gate, both are 0, output is 1. 0x is x and output is x1. Different 1. So it should be x1 is represented as this is don't care 1. So u1. Next question. A slow to fall transition, slow to fall, that is this transition, fault at a node Z can be modeled by. Whatever is this value, we want to apply to get this transition. So we want to have a transition of 1 here and a 0 here. So 1 at the frame 1 and 0 at the frame 2. So option A. Next question. The output of NAND gate and the output of NOR gate. We have a NAND gate, a NOR gate, and it's given x dominant 1 y. So this, if it is going to, this is x1, this is going to OR gate, and this is y1, this is OR. And the inputs are A, B, C, and D. We have to say if the value of y is 1, which of the following input combination should be applied? So y is 1. This is 1. Okay. So if we have 0, 1, 1 0. This will be 1 0. So this will be 1. This will be 1. So even A can be applied. B is 1 1 0 0. NAND gate, both inputs are 0. Sorry, both inputs are 1, output is 0. For now, it is 1. So this output is again 1. This output is 0. So again, this pattern can also be applied. And next, 1 0 0 1. So 1 0, this is 1, and this is 0. So again, this will be 1, and this will be 1. So both this also y will be 1. So all the three can be applied. Next question, choose the relevant statement above and deduct fault. So fault coverage remains the same, yes. Defect coverage increases, that means we can have, yes, it is all of the above. Defect coverage increases because say stuck at fault we have n deducts and that could have been deducting some other bridging fault. So the defect coverage increases. By changing the fault dropping criteria, now instead of one fault, if we one deduct, we have two deduct. In the ATPG, we will keep in the fault list for until and like we get two faults. So the normal ATPG can be converted to n deduct ATPG. So answer is all of them. Next question, select the correct best category which are best described by the following statement in the given order. Circuit operation is in ideal mode while analysis is in progress. It is called concurrent. Wait a second. Sorry, not concurrent. It's ideal. So non-concurrent. And circuit operation is in normal mode. When it is in normal mode, we say concurrent. It is suspended. That means the circuit operation is now off. We are like going to the test mode. So it's offline. So the correct answer is option A. Next question. For the following LFSR, find out the time period T if the initial output of D flip-flop is 0001. MSB is the output for the leftmost D flip-flop. So this is the one. It is MSB is the leftmost left. Try this question. Let's try this considering both. Now if it is 1001, we have to take the XOR of this 0 0 XORed with 1, it is 1. Shifted 1, 0, 0. Next, again this and this is 0. With this, it's 1. So 1, 1, 1, 0. Next, 1, 0 is 1. 1 and 1 is 0. 0, 1, 1, 1. Next, this 1 and 1 is 0. With 0, it's 0. 0, 0, 1, 1. Next is 1, 1 is 1. 0, which is 0, 0, 0, 1. Next one, this is 1. Here 1, here 0. So it's a 1. 0, 0, 0. So it's 1, 2, 3, 4, 5, 6. So total 6 patterns. After that, it is repeating. This is how it is given in the question. M must be is the leftmost D flip-flop. This is my left, so this will be the initial condition. Now this just we will try. These are 1, 0, 1. So answer is 6. This just we will try. If we could have considered in this way. So 1, 0 is 1. With 0 is 1. 0, 0, 0. 0, 0 is 0 with 1. It's 1. 0, 0 with 1. 1. And 1 with 1 is 0. And 1, 1 is 0, 0, 0, 0, 1, 1. Again 0. So 1, 2, 3, 4, 5, 6. Here also 6 patterns. After that, it repeats. Is this question clear? Yes, next question. Select the correct statement about LFSR. XOR gates are placed between the flip-flops, then it is called modular LFSR. It is correct. Complete LFSR is capable of coming out of all zero state. Yes, option D. So n degree polynomial LFSR called a primitive if it has time period n to the power n, so it's all of the above. In the n total number of inputs, W represents the width and for which exhaustiveness is needed, then which of the following are the N and W combined for a combined to be effective? So we said it will not be effective if this here we have written the condition. Combined LFSR I wrote somewhere the condition. Yeah. W greater than N by 2 will not be effective. W greater than N by 2 will not be effective. So first is 10 is greater than 17. So this will not be effective. 10 okay, no. W is 5 which is not greater than 10. So this will be effective. 13 is greater than 10. This will not be effective. 7 is greater than 5. Again, this will not be effective. So option B is. So where N is 20, W is 5. Clear? We will solve some more questions related to delayed fault. So robust path delay sensitization means if we have a R1 which is a like rising transition For an AND gate, this is controlling to non-controlling. So this values can be V1. So what will be this? R1 is fixed and the next is 1. So it will be this rising transition there. Similarly, if we have a falling transition here, then this should be strict 1, both. Like both should be 1, 1 because this is a non-controlling value. So the output will be a falling transition. So these were the two conditions. I'm just summarizing it. Next, we take one example. A, B, and we consider it is non-robustly testable. That means only one delay fault is present. So if we have a transition here, this will give a transition here, this will be inverted, and these two transitions, because of this inverter, like if you consider this point, there might be some delay. So the output will be like this. So now, if we have an A like this, say some this point we are capturing. This is the A. The B is instead of transitioning here, it takes some time and then goes to 0. Now see this transition time, it will go to 1 and 0. So in this capture phase, where it is capturing, it is 0. So it's a correct value. But because of some delay, if this is going till here, then the C value will be this edge is not affected, but it will go discharge to here, to 0 here. So when we are, and there will be some delay for that gate also. So this place, when we capture, we will get a 1. So here we will have the faulty response. So this is testable non-robustly. Let's see one more example for robust test generation. This question is taken from the Essentials of Electronic Testing book. Okay, now let's just name this Q, H, R, J, G, E, K. ABC, E, Q, G, H. Okay. So now if we have a transition, falling transition here at B, so this can be represented as F0. Now we want to propagate this transition to the output. The idea is that if any one of the gate is having more delay, that will change this transition, that will delay this transition. Now we want this F0 here. To get this F0 here, this is a controlling value, so it can be U0. So C should be U0. Now This is F0, and after this inverter, it will become a rising transition. Falling will become rising transition. And if this F0 is like generally interpreted as U0 for off path logic. That means U0 means it is don't care X, and falling transition means it's like 1 to 0. So we can write here U0. Now what we want here, this is a rising transition. So this is a transition. This is a non-controlling value. Non-controlling means it should be strict to 0. Yes, you can try. I will wait for a few minutes then. You got the answer? Any doubts? So here it is a non-controlling value. So we need a strict 0 here. To get a 0, 0 here, and yet so any one of the output is 0, then the output will be 0. So we need a strict 0 here. So these are the vectors. So that means A is strict 0, which is 0, 0. B is a falling transition, and C is U0, which means this is a falling transition 1 to 0, and U0 is X0. So what is V1 and V2 vector? V1 is 0, 1, X, and V2 is 0, 0, 0. These are the test patterns. Any doubts? Is this question clear? At K we will get R1, right? Yes, at K we will get R1. We will get this rising transition. And if this node had some delay, then it could have delayed this transition. So in this way, we will be able to detect this fault. Like we have propagated the not this node but this path. Yes, K will be R1. Any other questions? If this was non-robust, This is already like relaxed only. So if we have like non-robust, it could have changed to U0, so it's already U0. And the other one is this is needed so that it can be propagated. So I don't think so there will be any changes for this particular example, because this is S0 is needed to propagate this transition, whatever the method is. And here it is already user. If it was S0, then maybe non-robust could have changed to U0. I hope I have cleared it. Yes. Okay. Any other doubts? If no other doubts, then we can end today's session. Thank you so much for joining.